Hello, everybody. I'm Captain Mamgan. Start off with astronomical navigation. Talk about celestial sphere today. The inverted bowl, which you see, the sky, is the celestial sphere with infinite radius, with Earth being the center, on which are situated all our planets and all the other celestial bodies. On Earth, we had talked about the poles, the axis, the meridians, parallel of latitude, equator. Now, if we project them on the celestial sphere, where the axis would meet the celestial sphere are referred to as celestial poles. Here, what I'm showing you is the north celestial pole. Other side would be the south celestial pole. A great circle drawn on the celestial sphere in the same plane of the equator, we refer to it as equinoctial. Small circles, semi-great circles joining the poles, which we refer to the meridians on Earth, are referred to as celestial meridians here when we are talking about the celestial sphere. Small circles with the plane of on the plane of the parallel of latitudes are referred to as declinations. Declination circle, parallel of declinations. So declination is basically corresponding to the latitude. So it is the latitude of a heavenly body on the celestial sphere. We talked about celestial meridians. So here are two celestial meridians. One is your Greenwich celestial meridian, and another is just a meridian here, through which is passing through two celestial bodies here. And parallel of declinations, small circles parallel to the equator, equinoctial. Declination is the arc of the celestial meridian contained between equinoctial and the body. It is corresponding to the latitude on Earth. Greenwich R angle is the arc of the equinoctial or angle of the poles contained between Greenwich celestial meridian and the meridian celestial meridian passing through the body, measured westwards. So if this was the case on the Earth, this would be the longitude of an observer west. So GHA here is the longitude of the celestial body. So the two coordinates to give me the position of a celestial body is one is the declination, another is the GHA. And GHA, unlike what we measure longitude east and west of Greenwich, GHA is measured only westwards, and that is the clockwise direction. Here I have an observer who's on the east longitude, and we know the longitude is arc of the equinoctial or angle of the poles. Local R angle is the angle at the poles or arc of the equinoctial contained between celestial meridian passing through the observer and a meridian passing through the celestial body. If it was a case of Earth, this would be the D-long between these two meridians. Here we refer to it as LHA. And here you can see that LHA would be GHA plus longitude east. Now let's have an observer on the west longitude. LHA we said is, or the GHA, whatever, all the angles are measured clockwise. So LHA for observer on the western longitude would be going right round the poles and coming back here in the clockwise direction. Now we can see that LHA plus P1 would be 360. The total angle is 360. So LHA is 360 minus P1. And what is P1? Longitude minus GHA. So we come to the conclusion that LHA is equal to GHA minus longitude west here. So this is an important relation between GHA longitude and LHA, which is going to be used quite often uh, in celestial navigation. If I draw a line from the center of the Earth to the center of the celestial body, it will cross the Earth somewhere, and this position where it is touching the Earth is referred to as geographical position. On Earth, the coordinate should be the latitude and the longitude. But as just we saw here, the coordinates on the celestial sphere would be the declination and the GHA. So the coordinates for the geographical position are the declination as the latitude and GHA as the longitude. Now, ecliptic is a great circle on the celestial sphere. It is in plane with the Earth's orbit around the Sun, or we can call it as the apparent path of the Sun around the Earth. A point where the ecliptic crosses the equinoctial when the Sun is going from south to north is referred to as first point of Aries. So the third angle we talk here is SHA, sidereal angle, again measured westerly between the meridian passing through Aries and the celestial meridian passing through the celestial body. GHA Aries, what we talked about GHA, from Greenwich to Aries, measured westwards, angle at the poles or arc of the equinox. Here we can see that the GHA would be the sum total of GHA Aries and SHA. In nautical almanacs, when we'll be solving some problems, we'll see that the GHA of sun, moon, planets is given, but not for stars. For stars, he gives us SHA. And to obtain the GHA of star, I would have to add GHA Aries. So my GHA star is SHA star plus GHA Aries. And this relation just takes a little change here. That instead of just having GHA, we use GHA Aries and SHA star for stars. This is an important relationship which we got to remember always. If I was looking at this from top of the celestial pole, right, somewhere high up in the celestial sphere, I would see the pole and the equinoctial being the great circle, being right in the center, and all the meridians radiating out from the poles. So here I'm just showing you some Greenwich meridian and the meridian passing through the body, and observer on the east side. As just defined, Greenwich hour angle is the angle at the poles between Greenwich and the meridian passing through the celestial body. And this DPO is the longitude of the observer. LHA we just defined is the angle between the celestial meridian of the observer to the celestial meridian of the body measured westward. So we can see that the LHA would be GHA plus longitude east. Now let's say an observer on the western longitude, The longitude would be from Greenwich to the observer. And the LHA, as we stated, is from the observer's meridian to the meridian through the body. Now the sum total of this is 360. Here, if I subtract P1 from 360, that should be the LHA. And P1, angle P1 is longitude minus GHA. And we arrive at the equation here. GHA, LHA is equal to GHA minus longitude west. Now when we talk about stars, we talked about first point of Aries and SHA. SHA is from Aries to the body, meridian through Aries, meridian through the celestial body, and measured westwards. And GHA Aries from Greenwich to the first point of Aries. As you can see it here, the GHA is the angle or arc between Greenwich and the meridian, celestial meridian through the body. Now SHA plus GHA Aries minus GHA star would be 360. As you can see, from here to here plus here to here is 360. This has been added up in GHA Aries. So if I subtract GHA star, it should be 360. And I come to the conclusion that GHA star is SHA plus GHA Aries. So GHA star is GHA Aries and SHA star. Now all these things what we talked about, the declination, the LHA, GHA, SHA, they all arc of equinoctial and measured westwards, except declination, which is north and south. Now position on the earth is given by the coordinates of latitude and longitudes, which when we are measuring it are in the reference of two great circles. One is the equator and another is the prime meridian. On celestial sphere, we have different systems to have a fix on the position of a heavenly body. In equinoctial system, which we just discussed, the reference points were taken as equinoctial and celestial meridian. So the equinoctial system is having reference of great circles as equinoctial and the celestial meridian. And what do we have in equinoctial system? SHA, GHA, LHA, RA and declination. This RA I have not mentioned here earlier. RA is an angle which is measured, it's the only angle which is measured eastwards from Aries to the body. SHA was measured westwards from Aries to the body. So sum total of RA and SHA is 360. So 360 minus SHA is RA. RA is not used by navigators anymore. It's used by astronomers and it has been replaced by SHA. So we do not really come across RA much, though in some questions we'll come across this. So it will suffice for you to understand that RA is 360 minus SHA. The other system what we use in navigation to fix the position on the celestial sphere is the horizon system. In horizon system, the reference is taken up from observer's rational horizon and observer's celestial meridian. And the coordinates what we deal with are the true altitude and azimuth. Now, here, this is the observer and his position is with the coordinates of latitude and longitudes. And this is your celestial sphere with the celestial poles and the meridians starting from P to P dash on one side and P to P dash on the other side. So on the side of the observer, that's the observer's meridian. The other side, which is 180 degrees opposite, is the observer's inferior meridian. And equator projected on the celestial sphere equinoctial. Now, if I draw a line from the center of the Earth through the observer, wherever it meets, we call it as the zenith. Zenith is the point right overhead the observer, and the point 180 degrees opposite, we refer to it as nadir. Nadir is not used in navigation much. We'll be dealing with zenith most of the time. Now, zenith would be the position of the observer on the celestial sphere, as P, Z, Q, P dash is the meridian of the observer, and Q to O was the latitude, and that has been substituted by ZQ here. That's the latitude, so that's the position of the observer on the celestial sphere. In horizon system, we talk about vertical circles. Vertical circles are great circles drawn from zenith to nadir. They join zenith and nadir, and as we know that we can draw n number of great circles as long as the points are on the extreme ends of the diameter. So we can draw as many great circles as possible from great circle from zenith and nadir, vertical circles. Now this is a vertical circle. The second thing what we talk about is the rational horizon. Rational horizon is a great circle. All points are 90 degrees from the zenith. The point closest to the north pole is the north of the rational horizon, south closer to the south pole, and then going clockwise from north, east, south, west. So this is a diagram what is being seen from the west side you're viewing it from the west, and this type of a figure what we'll be drawing are called to be drawn on observer's meridian. So the coordinates in horizon system when we talk about is altitude and azimuth. Observer's prime vertical, a vertical circle which passes through east and west of the rational horizon, is your prime vertical. Altitude is the arc of vertical circle. Let's have a vertical circle passing through a celestial body. It's an arc of the vertical circle between rational horizon and the center of the body. So this is your altitude. The second coordinate we talk about is azimuth. Azimuth is the angle at zenith contained between the observer's meridian and the vertical circle passing through the body. Angle Z is your azimuth. So these are the two coordinates what we talk about in horizon system. Now in navigation we use the combination of equinoctial system and the horizon system to solve and obtain our position. From zenith, all points are 90 degrees from the rational horizon. So this being the altitude remaining of the vertical circle would be 90 minus altitude, which I have written down as ZD. It is referred to as zenith distance. And this is the meridian passing, celestial meridian passing through the celestial body, and the angle at the pole between the observed meridian and meridian passing through the body measured westward is called the LHA. Q to Z is the latitude. So P to Z would be 90 minus latitude. Then we set the small circle parallel to the equator passing through the body, declination circle. So this is your declination. From pole to equator is 90. So the remaining side px, the polar distance what we call would be 90 minus declination. So now you can see that in this triangle I have used both the system, the altitude, azimuth, R angles and declination. In navigation, of course, there is another third system, ecliptic system, in which the measurements are done from the ecliptic, not used by the navigator. So I'll just skip it for the time being. Now this is the figure what I showed you, drawn on observer's meridian seen from the west. This is what is your national horizon, all points are 90 degrees. If I was just drawing your national horizon, it would appear something like this, with the prime vertical passing through east and west point of the national horizon. Now let me just bring zenith to the center and move it down. So zenith would appear somewhere in the center, and now you can see that all points are 90 degrees from the zenith. When I moved the zenith, along with it, all these things will also move down parallel to the zenith. That's your pole, the body, the equator, and the meridian. They all come down to the national horizon, and they would appear something like this. And with the meridian joining north and south, the way it is joining here. Equinoctial, great circle. We saw the zenith was here, equator was here, south of the observer, south of the observer. Now here the observer is north latitude, because from Q to Z is the latitude and Z is north of the equator. Altitude we talked about, arc of the vertical circle from rational horizon to the center of the body. So Zx is 90 minus altitude, because all points are 90 degrees from the rational horizon. And the angle at zenith contained between the observer's meridian and the vertical circle is the azimuth. So these are the coordinates used in rational horizon, rational on the horizon system. Talked about declination circle, small circle parallel to the equinoctial. From pole to equinoctial is 90. This is declination. So P to X, the polar distance would be 90 minus declination. And the angle at the poles between observer meridian and the meridian passing through the body measured westward LHA. So here I have used even the equinoctial system to get this triangle. Z to Q was the latitude, so PZ would be 90 minus latitude, as pole to equator is 90, so PZ would be 90 minus latitude. This figure, what I have drawn here, is said to be on observer's rational horizon. This was on observer's meridian. Thank you. We'll continue from here.